last topic of Unit 5, which is nothing but a type of autoencoder called variational autoencoder. I've already discussed all the features and principle of autoencoder along with its block diagram to you. Now we are going to see a variational autoencoder. So basic autoencoder, which I've already discussed to you, takes an input and converts it into a hidden variable z, which is in latent space. That means the dimensionality is reduced. That is encoding. And what is happening on the other end is it takes the hidden variable and generates or reconstructs back the original input as x bar. So that's a decoder. So this is actually a discriminative model, the basic autoencoder. It is not a generative model. Okay, so autoencoder, if you see, it has emerged as an architecture for data representation and generation, but variational autoencoders stand out, where variational autoencoder introduce probabilistic encoding and it is used in diverse applications. Now, if autoencoders, they are neural network architectures that are intended for compression and reconstruction of data, which I already explained you. It will be consisting of an encoder and a decoder, and the encoder will aim to learn sufficient data encoding from data set and pass it on to the bottleneck architecture, the remaining architecture. And the other part of the autoencoder will be a decoder, which will use the latent space, that is the reduced dimensionality hidden variable, and then use it in its own bottleneck architecture to get back the regenerated image or reconstructed image, which is similar to the input. Now you try to reduce the loss function, that reconstruction error function, for optimization, correct? That's your normal functioning of autoencoder. Talking on variational autoencoder, which was proposed in 2013 at Google and Qualcomm by Max Welling and team, VAE gives you a probabilistic approach to autoencoding. So a variational autoencoder will provide a probabilistic manner for describing an observation in latent space. That is, whenever you want to step down the number of dimensions of the input data, you can go for a probabilistic manner for that, and for that VAE is popular. So rather than building an encoder that outputs a single value to describe each latent state attribute, you will formulate an encoder to describe a probabilistic distribution for each latent attribute. So VAE in a nutshell is an autoencoder whose encoding distribution is regularized during training in order to ensure that the latent space that you are generating has got good properties, which allows us to generate some new data. Basically, it gives a probabilistic approach to the original autoencoder. Therefore, it is suitable in the applications as synthetic data creations and data compression. Now, what is the principle of VAE? VAE is different from AE, AE, that is autoencoder, in a way that in place of representing a single variable in the latent space like Z that we were discussing, in place of a single variable, it provides a statistical manner or a probabilistic manner for describing the samples of data set in the latent space. So what happens here is it will output a probabilistic distribution, the encoder. Whereas instead of giving the variable in the latent state, it is going to give you probability distribution in the latent space. Also, you have got a decoder, and both of them work together to minimize the reconstruction error. You always want to achieve the optimization, but you can introduce some regularization of latent space, and if you want to introduce that, you have to have a little modification of encoding and decoding process. That means if you want to regularize the autoencoder pattern process, then you have to, instead of encoding an input as a single point, you have to encode it as a distribution, probabilistic distribution over the latent space. That's the biggest difference between a normal autoencoder functioning and variational autoencoder functioning. So the principle of VAE is based on combining the concepts of variational inference and neural network to learn a probabilistic mapping between input and latent state. So you can see you can say that VAE is a probabilistic latent variable model. So VAE assumes that the input is generated from an underlying probabilistic process involving latent variables. So the goal is to inform distribution of these latent variables given the observed data. So, and you have to understand the this particular thing a little properly. So as what I said is, you have got as in a normal autoencoder, if I say you have got an input, you create a Z. You have a high dimensional data, you create a low dimensional data, and then this part is your encoding, and inside decoding takes the low dimension data, gives you high dimension data, right? But gives you latent. This is called latent space. Whenever you are reducing the dimension, so you have got a latent. Whenever you are reducing the dimension, you have got a latent space, wherein you create a latent variable. This happens in a normal autoencoder. What we are doing here in a variational autoencoder is, instead of generating this variable, you will give you a probabilistic distribution of these latent variables. With this, you can achieve regularization. Okay, so that's the difference between normal autoencoder functioning and a variational autoencoder functioning. So that's the difference in the principle. That's what I can say. So now what happens inside training is, first, as usual, input is encoded, but encoding is like a distribution. You can see here changed in the representation. Earlier I used to write only Z, but here I am writing P of Z by X. Okay, so this is input is encoded as distribution over latent space. Second, a point from latent space will be sampled. There is sampling which is going on, and then reconstruction error can be computed. So reconstruction error is back propagated throughout the network to achieve optimization. So that's the entire process. So you can see training of variational autoencoder is completely different than a normal autoencoder. So this is exactly a VAE architecture that I was explaining you. X undergoes encoding. It undergoes a probabilistic distribution approach, wherein a single sample will be taken and it will be sampled and it will be reconstructed back so as to calculate reconstruction error, and then give it back in a back propagation to get a properly reconstructed image or output at the end of the decoder. So I can elaborate this architecture as components of VAE, wherein first I am going to discuss on encoder, takes the input data and maps it onto the probabilistic latent space. So input layer accepts input data, which can be a vector. Hidden layers will have fully connected layers or convolutional layers if you are dealing with images. So you will reduce the dimensionality of the input here and capture some features. You have got, as you can see, the mean and the variance layer also inside the encoder. So two separate layers, which are mean and variance, are useful in representation of latent distribution of these latent variables, and these parameters define normal distribution from which latent vector will be sampled. So next is what you have got is a sample layer. So what is happening in sample layer is reparameterization trick happens, wherein a layer that samples from a normal distribution using mean and variance obtained from previous layer, and then you have got latent space, which is going to sample a particular variable of latent space. It is a lower dimensional space, the latent space, wherein each point is going to represent a potential encoding of input data. Output is going to be a latent vector, and it represents a particular sample in the continuous latent space. Once that sample is taken, it is given to a decoder. It takes a particular sample from the latent space and it reconstructs the input data. Again, the decoder is again a neural network. It has got an input layer wherein you have one sample, hidden layers, which will help you to increase the dimensionality of the data to get back your original data. Finally, you have got an output layer which produces the reconstruct data, which should be similar to your input data after compression. Lastly, as usual, you will find out reconstruction loss function, and which is going to find out the difference between input data and reconstructed data through binary cross entropy or mean square error. Sometimes you can also go for KL divergence loss, which will help you to find out the difference between learned latent distribution and prior distribution, and you pass it on in back propagation to optimize your neural network model. Thus, you will achieve a regularized model, encouraging the latent space to follow a specific structure. So, this was about VAE. It's very different from a normal autoencoder. So, a little patience. and efforts will be required by you to understand a VAE model better.